This is topic 1, lesson 8. In this video, we're going to talk about the molar volume of a gas. The objectives for this lesson are be able to describe Avogadro's law and how it relates to gas volume, and be able to solve stoichiometry problems involving gases. So let's review a little bit about what we know about gases from 10th grade chemistry. We know that gas particles are moving fast, constant random motion. We know that there's a lot of space between the particles themselves. So if we look at the picture below, we have red circles representing one gas, and we have blue circles representing another gas. If you look at the amount of space between the particles, you see that there's a lot of space between the individual particles. There's more space between them than the amount of space they actually take up. So gas particle volume is considered to be negligible. They have negligible forces between them. So even though they're different gases, there's still more space between them than the amount of space that they take up. Also, the chemical nature of the gas is irrelevant to its volume, which means that it doesn't matter what the gas is. It could be krypton, and this could be, one could be krypton, and let's say the red could be helium. It doesn't matter what the gas is. The key idea you want to take away is thinking about when you have a gas, there's more space between the particles than the amount of space it actually takes up, regardless of what the gas is. We also want to recall Avogadro's law. Avogadro talks about the fact that if you have equal volumes of gases, if they're measured at the same temperature and pressure, they're going to contain equal number of molecules. So we saw questions in 10th grade chemistry where you had different gases, let's say oxygen and chlorine, and it didn't matter what the gas was. If they were both measured at the same temperature and pressure, we could say that they both would have the same number of molecules. So we need to be familiar with Avogadro's law. Avogadro is stating that volume is going to be proportional to the number of moles for any substance at a constant temperature and pressure. So that's important that you have this constant temperature and pressure. It doesn't necessarily have to be STP, but as long as you have the same temperature and same pressure, the volume will be proportional to the number of moles. You could look up the values for standard temperature and pressure in your data booklet, and that's important as we move forward. We're familiar with this 273 as standard temperature. Here, standard pressure is 100 kPa. So whereas in the 10th grade curriculum, we talked about 101.3, it was restandardized by IUPAC, and IB is more on track with modern updates. So 100 kPa, we want to make sure we're using that value. The molar volume of a gas, which means that how much 1 mole of any gas at STP will occupy. You could use either value here for meter cubed or decimeter cubed. Probably more often going to see the decimeter cube value, so 22.7 decimeter cube per mole. So the volume of any mole of gas at standard temperature and pressure. And you might have learned 22.4 in honors chemistry last year, but the reality is what 22.4 is matching to the 101.3 that you would have done in 10th grade. So we want to familiarize ourselves with the units that IB will be using. So 100 kPa corresponds to 22.7 decimeter cubed. Okay, so let's look at an example of how we could apply the molar volume of a gas to a stoichiometry or a mole problem. So first example, calculate the number of moles of chlorine gas in 25.5 decimeter cubed at STP. A couple things to note, the decimeter cubed value here is telling you the volume, and also that we're at STP. So remember that whenever you have a gas at STP, and we have chlorine gas at STP, we know that the molar volume is going to be 22.7. So you start by writing your given 45.5 decimeter cubed. We multiply by 1 mole over 22.7 to get our decimeter cubed to go away, and we're left with 2 moles of chlorine gas. Okay, let's look at another example. Here we want to calculate the volume in centimeter cubed. Keep the units in mind always. Occupied by 3.20 grams of carbon dioxide gas at STP. So just something that maybe we would just want to start to think about every time we see a problem that says gas and an STP. Maybe you just want to annotate on your paper or write down 22.7 decimeter cubed to keep in the back of your mind. So we start with our given. What is our given? 3.20 grams of carbon dioxide. We take our grams and we go to moles. So we multiply by 1 over 44 because 44.01 is the gram formula mass of carbon dioxide. We get to moles. Once we have our moles, we convert our moles into a volume and we get 1.65 decimeter cubed. The question doesn't want decimeter cubed, the question wants centimeter cubed. So you can then take your decimeter cubed and multiply by a conversion factor. This is in your data booklet, and you get the value for centimeter cubed. All right, our next example. What volume of hydrogen gas is produced when 0.6 moles of magnesium reacts with excess acid at STP? So what we did first is we want to write out the equation. So we write out magnesium plus hydrochloric acid. We get magnesium, chloride, and hydrogen. The equation is then balanced. we start with our moles of magnesium. We have 0.06 moles of magnesium. Okay, so we start by converting the magnesium into hydrogen because our goal is to find the volume of hydrogen gas. So I'm at magnesium, I want to get to hydrogen. So we take our magnesium and convert it to hydrogen. So it's just a mole-mole ratio. And we get 0.6 moles of hydrogen. So it's a 1-to-1 ratio essentially. What we're then going to do is take our moles of hydrogen and convert that to volume because that's the goal, is to find the volume. So multiply by 22.7 decimeter cubed per mole and we get the value for 1.36 decimeter cubed. Okay, and here's our last example for this video, and I guess probably the most challenging. So we could then take what we know about molar volume, 22.7 decimeter cubed per mole, and we could apply it to problems involving limiting reactant. So here's our question. At STP, okay, you notice STP, 30 centimeter cubed ethane reacts with 60 centimeter cubed of oxygen. Which reactant is present in excess? How much remains after the reaction? And what volume of CO2 is produced? So first we write out a reaction of ethane and oxygen. Water and carbon dioxide are our products. You might want to recognize at this point there's a combustion reaction. We have oxygen as reactants, CO2 and water as products. All right, so first step is to determine the limiting reagent. And we also want to find what's in excess. So we take our values, 30 centimeter cubed and 60 centimeter cubed for oxygen, and we're going to convert them into moles. Would be the first step, right? Because we're in volume and we'd want to go to moles, and then we would want to go to moles of our product. Here we're looking at CO2 because they're asking how much CO2 can be produced. So we are, when we do molar volume problems, since we have centimeter cubed here, we'll bring it up now. When you have a volume problem, we can convert the volume into moles, and then we can convert the moles to moles, and then we can convert the moles back to volume. But to get the volume value to moles, I'm dividing by 22.7, and then I'm going to go to moles, and then to get out of moles and go back to volume, I'd have to multiply by 22.7. So it's okay, whenever we're going to deal with volume problems, and you're going from volume of one substance to volume of another, we don't go volume, moles, mole, mole, then mole back to volume. You just multiply by the mole ratio. So if I'm at 30 centimeter cubed, the mole ratio here for CO2 to ethane here is going to be 4:2. So I'm just going to multiply by the mole ratio, and that tells me what the volume is of CO2. So I didn't go volume to moles, moles to moles, and then moles back to volume because I'm dividing and then multiplying by 22.7. So anytime you're going from volume of one substance to volume of another, we're just going to do a mole-mole ratio. So for oxygen, we're going to do the same thing. We start with 60 centimeter cubed. We're just going to multiply by the mole ratio. So the mole ratio of CO2 is 4/10. If you don't believe me, you could do the math out on your own by going from volume to moles, moles to moles, and then moles back to volume. But from now here on out, volume stoichiometry problems, you could just multiply by the mole ratio. So when we do this, we see that oxygen only makes 24 centimeter cubed. So that means that oxygen is the limiting reagent, and ethane is going to be the excess reagent. So we figured out what's the limiting, what's the excess, but now we need to know how much remains. So remember, to figure out the remaining, how much is left over, what you do is you figure out how much you actually used, and then you're going to subtract what you were given. So here, since ethane is an excess, we were given 30 centimeter cubed of ethane, and we just got to figure out how much ethane we used. So it's going to work out to be 12, but let's show you how we get that 12. To figure out how much we used, what we're going to do is look at our limiting reagent. All the limiting reagent was used up. So our oxygen, our 24 here, was all used up. We have to convert that into how much excess we used. So all 60 centimeter cubed of oxygen was used. Let's convert that oxygen into ethane so we could figure out what that corresponds to. 60 centimeter cubed, and then I do a mole ratio from oxygen to ethane. So I have 2 moles of ethane over 10 moles of oxygen. Tells me that we actually used 10 centimeter cubed of ethane. So subtract the 30 that you were given minus the 12 how much you used, and you get 18 centimeter cubed. Okay, so in summary, you were supposed to, at the end of this video, be able to understand what molar volume of an ideal gas means. Know that it's in the data booklet too. We should know that Avogadro's law helps us enable to figure out mole ratios. And we need to be able to solve problems that are going to involve volumes of gases using Avogadro's law.